conjugate acid-base pairs and relationships between Ka, Kb, and Kw. Okay, so let's just quickly remind ourselves of conjugate acid-base pairs. If you put an acid in solution, you're going to get a conjugate base. So hydrofluoric acid is going to yield fluoride anion as the conjugate base, and it's going to produce hydronium. So the proton is donated to water, producing that hydronium. When we have a weak base, or any base in solution, the base is going to accept a proton from water. So water is acting as an acid, and we're going to produce a conjugate acid and hydroxide. Now also remember that for a weak acid, or a weak base for that matter, there's an equilibrium between the weak acid and its products, and we can write an equilibrium constant expression that we call Ka. So this is the acid dissociation constant and the equilibrium constant expression for this weak acid dissolved in water. Now let's take a look at a specific weak acid, and this is acetic acid. This is what is in vinegar, and we're going to dissolve it in water. So here we have acetic acid, and the reason why it's written this way is just to give you an idea of the structure. So these three hydrogens are bonded to the carbon. That carbon is bonded to this carbon, which is bonded to both of those oxygens. So one is double bonded, and then the other one is single bond, and then this hydrogen is bonded to one of those oxygens. So you can kind of see that down here. So writing it this way gives you an idea of how it's bonded together. So here is our losable proton. So this is the proton that is lost when we put acetic acid in water. And so the equilibrium is between the conjugate base, and so basically that's whatever's left over after that proton is lost, and hydronium, because acetic acid is a weak acid. What if we were to isolate that acetate, so the conjugate base, what if we were to take that and put it in water? We would get conjugate acid, so acetate would have a proton donated from water to get conjugate acid, which would be acetic acid, and hydroxide. And so in this case, here we have acetate, and here is the proton that is gained by acetate to produce acetic acid. Now, what we've been talking about is that this acetic acid and acetate are conjugate acid-base pairs. And so I've given you the Ka value for acetic acid. And we saw that we could also isolate the acetate and put it in solution. And the Kb for that equilibrium is 5.68 times 10 to the negative 10. So Ka for acetic acid, 1.76 times 10 to the negative 5. Now these guys have kind of a special relationship. Because if we multiply them together, we're going to get 1 times 10 to the negative 14. So remember, that is the value for Kw at 25 degrees C. So a new relationship that we have to interconvert between Ka and Kb for conjugate acid-base pairs is Ka times Kb is equal to Kw. So that means if we have a Ka, we can always get Kb if we're dealing with the base form. If we have Kb, we can always get Ka if we are dealing with the acid form. So we can interconvert using Kw. So Ka is equal to Kw divided by Kb, and Kb is equal to Kw divided by Ka. So we can interconvert using Kw, which is very, very handy. Just showing you the filled-in expressions. So if you do the math, you're going to find out that if you take Kw and divide it by Kb, you're going to get this value. And then the other way around, of course. Take Kw, divide it by Ka, and that'll give you this Kb. Now, we can also calculate something called a pKa for an acid. And we do that in the same way that we've calculated every other p something, and that is just take the negative log of it. So if we take the negative log of Ka, we're going to get pKa. And if we calculate the negative log of Kb, we're going to get the pKb. So these are often used for convenience because it's much better than having some scientific notation number to deal with. You'll see pKa's used very often, as well as pKb's. Now let's do a quick little example. Let's calculate the pKa for our acetic acid. So if we take the negative log of the Ka, which is 1.76 times 10 to the negative 5, we're going to get 4.75. And same with the pKb, plug in the Kb, and we're going to get 9.25. So that's an example. Now what if we have the pKa, but we want the Ka because we're doing an equilibrium problem? Well, luckily, we can just take the inverse log of it. So 10 to the negative pKa is going to give us our Ka back. And 10 to the negative pKb is going to give us our Kb back. And we already discussed that we can get Kw back by doing the same thing. And also, just remember that at temperatures other than 25 degrees C, Kw will have a different value. So just be aware of that. Most of our problems will just be at 25 degrees C. Now, here are a few more relationships. So it's kind of interesting. If we take pKa plus pKb, then we can get pKw. So again, at 25 degrees C, pKw is equal to 14. So pKa plus pKb is equal to 14. That's also very handy in interconverting. All right, next we're going to talk about the conjugate seesaw and analyzing Ka and Kb for acid or base relative strength. So we're going to use those values to figure out the relative strength of a weak acid or weak base.